Don't lose heart on it. So let's begin. I'm going to put a timer on. One of my videos went over 60 minutes the other day, and it makes it really hard to sort things out. So I'll put my timer on for 50 odd, 55. And we'll take a break, I hope. So we'll see. So 55. So today we're going to do the second part on magnetism. Last time we did, what a magnetic field is and all that kind of stuff. And today we're going to talk about making magnetic fields. We're going to talk about a thing called Boyle-Savart law, which is, again, it looks horrendous, but because we're physics, we cheat like crazy and we do symmetries, and it's quite nice. And that's not just me. I swear it's not just me. I'm not just like... It's not that everybody else does it from first principles and I give you the cheat. It's like in the book as a cheat. And then we'll do some just interesting thing like force between parallel currents. We'll go on to Ampere's law. And I'd like you to kind of focus on Ampere's law. I'd love it if I can say to you, what is Ampere's law? And you're going to tell me what Ampere's law is by name, And then we'll talk about magnetic flux. Well, hold on. Didn't we do electrostatic flux? Yeah, we're going to use those same ideas over again. We're going to talk about Gauss's law in magnetism. Hold on, didn't we do electrostatic Gauss's law? Yeah, we're using it. If it worked on one, maybe it's going to work on another, because they're all fields. If it works on a field, it works on a field. And then we'll talk about this thing called displacement current, which again is, it's a little bit of a, it's to get us out of a tight situation. I don't really care that much about it, but I want you to know about it, so we'll go on. Boyle-Savart. So here we are. We have a piece of wire. And let's have a current flowing through that piece of wire. And let's have the bendy piece of wire. And then let's flick a point somewhere in the distance. And we know that as the current flows, let's just remind ourselves, if we have a piece of wire with a current flowing in it, we create a magnetic field. And the magnetic field forms loops around that. So it's almost like a, what is it, Swiss roll, I'd call it, a roly-poly thing. And the way you get the direction is you put your thumb in the direction of the current and your fingers at the direction of the magnetic field from north to south. And notice they don't start or end anywhere. We're so used to this idea that a magnetic field starts at the North Pole and ends at the South Pole. So we get used to that and we get, oh yeah, it kind of goes like that. But it never does end. It goes through the material. Well, okay, I can kind of accept that. But now we have this magnetic field where if I look at this wire and the current is coming towards me, then my magnetic field goes around that, like that, and it has no beginning and no end. And I don't know what you feel about it, but I feel very uncomfortable about that. That's just like, man, it's just existing in this like concentric circles. But that's the way it goes. Okay, so then the little bits of current in this little piece of wire will cause this magnetic field effect. But because we have a whole bunch of little pieces of current in a whole bunch of lengths of wire, I've got to somehow integrate those things together. And this just looks horrible to me. I can tell you now, this is just giving me goosebumps because it's going to be like, So what we're going to do? Well, the first thing to have is a good diagram. So I'm going to define a certain length of wire, delta S, ds, little length. And I'm going to have a certain current going through it. And then I'm going to have a point of interest, P. And I'm going to say, what's my little bit of magnetic field at that point? And to define that point, I'm going to point towards it. So I have my unit vector. And I have my separation, my distance. So I'm just defining my terms here. And what I'm going to say is, consider the magnetic field, little delta B, at a point P, caused by the current flowing through a length of wire element ds. So I'm just interested in this little ds bit. The position vector relating the length element ds to the point P is R. So that's my R vector. Now, I've not shown R on this diagram. I've shown the length, but if you imagine R being like that, and it goes from here to there, okay? There's my R. Yeah. Boyle-Savart says my little bit of magnetic field is equal to, this is mu naught. We've done epsilon naught before. What was that called? Well, that was called epsilon naught, wasn't it? What's it? If you looked it up in a dictionary, what would you look up? Permittivity. Permittivity of free space. Mu naught is like its twin, and it's the permeability of free space. Permeable means you can kind of like, you know, get, is it gases or liquids going through it? A permeable membrane. It's like got holes in it all over the place. I don't believe that's got anything to do with this. It's just, you know, that's the way I remember it. I'm thinking of a sponge permeability. But just know the two terms and know the two symbols. So it's permeability of free space over 4 pi. And then we have the current times ds crossed with r over r squared. And so we say where mu naught is the permeability of free space, and mu naught is equal to 4 pi times 10 to the minus 7 Tesla meter over amps. Okay, let's do the integral. And you get, well, you don't, we've got to just do the integral. We get, let's take out the common terms. I is constant for this piece of wire. Every little element has the same amount of current going through it. Mu naught's constant, 4 pi's constant. So take those out of the integral. So I get B, my total magnetic field at this point, P, is equal to mu naught I over 4 pi integral ds crossed with r over r squared. And that, my friends, is Boyer-Savart. That's the bit that you learn. Okay? And we're going to learn how to use it. Where did it come from? It came out of the hat. No derivation of it. It's just out of the hat. Boom. Here we are. Hate to do it, but that's the way it goes. Let's skip this. Oh, yeah. So, I'm sorry. This is, so a couple of semesters ago, I noticed that everybody was scribbling like crazy and people weren't listening. This was before we had the videos going. So my first approach was, I'm going to write down all the presentations, and then they won't have to copy like crazy because it's in their notes. This is in your notes. But, you know, frankly, and I'll talk about how it's done, but frankly, I don't like it as much. I don't know why I don't like it as much, but I just feel like it's a bit like, you know, the end of the story before the beginning. So it's, I don't know, maybe it's clearer. I don't know. I'll be interested in what you feel about it. But we'll do it. We'll contrast it. I'll see what you think about it. So this is the problem. We're going to take, and this is what we're going to do. We're going to take sections of a circle. We're going to cheat by symmetry. So I'm always going to ask you about a point of interest at the middle of some section of a circle. It could be an entire 360 degrees, could be a half a circle, could be a quarter of a circle, could be a third of a circle, could be 16/17ths of a circle. I guess it could be 2 whole circles, I don't know. But it's going to be a circle. I'm going to only ask you about the middle. I'm not going to go here, I'm not going to go down here, none of these places. I'm only going to ask you about the middle of the circle. And I'm going to say a current carrying wire is bent in a complete circle. In this case, use Boyer-Savart law method as taught in class to show that B at the center of the circle is B equals mu naught I over 2 pi over 2r, where I is the current flowing through the wire and r is the radius. So this is my radius, and I have a current, doesn't matter which direction it is. There's my current flowing. And I want B at the middle, so I want B at that middle point there. Okay. So how do we do it? And the first thing we do is we write down Boyer-Savart. So we write this down first. So it's B equals mu naught I over 4 pi integral ds crossed with r hat over r squared. Now, let's just remember, let's just think about it. So I've got the diagram down here already. So here's my ds. I got my current flowing in the opposite direction in this. Well, actually, I've got my current flowing down here. Okay, it makes no difference. So there's my ds from one side to the other. And then I have my R, and my R points from my point of interest towards the section that I'm imagining. So it points from the center to my ds. And the radius, I've shown it as little r squared here. It's big R squared on my diagram, so I'll get to that in a minute. And then I'm going to recognize a couple of things. And the first thing I recognize is that, well, I've already seen that mu naught is a constant, I is a constant, 4 pi is a constant. And then the thing I recognize is that R is a constant. Okay, that's kind of useful. So that in principle could come out of my integral. And the other thing I want to recognize is that my ds is tangential and r hat is radial. So these two vectors are at 90 degrees to each other by definition for this geometry. And so if I think about it, you know, A cross B is equal to magnitude of A times magnitude of B times the sine of the angle between them. And sine of 90 is going to be 1. So that's kind of nice because I go from, and so that means I can go from having vectors to having magnitudes. And then the other thing I want to recognize is that r hat is a unit vector, so r equals 1. Okay, so B is equal to mu naught I over 4 pi r squared. And then I'm going to turn around and say, well, so this integral of vector ds crossed with r is like basically the integral of ds times r times the sine of phi, and that equals 1, and that equals 1. So this is my integral of ds, isn't it? That just gives me my integral of ds. That's my integral of ds. Oh, that means that all I have to do is integrate the length, all the little ds's around my wire, which is the circumference, yeah, for a complete circle. So I have my mu naught, I have my I have my 4 pi r squared. R squared got took out because it's a constant. And then I have my integral ds is 2 pi r because it's circumference. This is the circumference. Okay. So that pi cancels with that pi, that r cancels with one of those. That cancels with that. I end up with mu naught I over 2r. Okay. In this case, my radius is equal to big R, so R is equal to big R. So B is equal to mu naught I over 2 big R. And isn't that what it asked me to prove? So it's a technique, isn't it? It works under very specific circumstances, as far as we're concerned. You could, on principle, you could use less symmetry and do more work. But we're doing so much stuff, we're going to keep to symmetry and, you know, do this. I would not ask you to prove this, I would ask you to calculate this. But the basic methodology, that process of write down Boyot-Savat, recognize that R is constant, recognize that ds is perpendicular to r hat and hat equals to 1, and then rearranging, recognizing that this is the length of the wire. In this case, the length of the wire is the circumference. And then substituting, that's the meat and potatoes of this. Yes?
Can you explain again why r hat is 1?
Oh, because it's a unit vector. By definition, yeah?
Oh, by definition.
Yeah, by definition it's 1. That's the nice thing about it. From a teaching point of view, I can do this. I can change the amount of a circle that I give you. I can change whether I give you R and have you figure out L. That integral ds is the length of the wire. Agreed? Or I could give you L and have you figure out R. Can you see how they're both involved? So I can go, oh, here's the length of wire that's bent into a circle, or a half a circle, or a quarter of a circle, or a third of a circle. Or here's a quarter of a circle of radius this. Can you figure out what the length is? So that I can go either way. Yeah? And that's the ring, that's the changes I can ring. So let's do one, actually. Yeah. I want you to do one. I'm going to kind of guide you through it a bit, but I'm going to put my clock on so you can race ahead of me and get this thing sorted out. So the first thing I'd like you to do is read through it. It says, let me change my colour pen so that it looks nicer. Let's go to light blue. I like light blue. So it says a current carrying wire is bent in a semicircle. Use Boyer-Savat law method as taught in class to determine the value of B at the center of the semicircle. So here's my semicircle. It says that assume a current flowing through it of 5 amps. So I is equal to 5 amps. And the radius of the semicircle, R, is equal to 2 meters. And I want you to find me my B here. And you're going to be using the method of Boyer-Savat as taught in class. So you're going to write down your equation. You're going to recognize that R is constant. You're going to recognize that R hat and ds are perpendicular to each other. You're going to recognize that R hat is 1. You're going to do the change and get integral ds. You're going to recognize that integral ds is now half a circle. And you're off to the races. We'll pause there while you do it. So here we are. I must confess that I always have to, when I start teaching this section, I've got to look up Boyer-Savat's. It's one of the equations that's still not, if you woke me up from my sleep, I couldn't tell you it. And, you know, it's kind of like the other equations that I can just tell you. This is one that I've always got to work on a little bit. And in time, it'll get more and more. If I did it for a living all the time, then I'd know it. But, you know, I do it once a semester. So it's B equals mu naught I over 4 pi integral ds crossed with R hat over R squared, yeah? So the first thing I recognize is that, can you see that? Actually, it just occurs to me that the sun's shining through this window, so let's go to a color that's a little bit easier to see. So then the next thing I recognize is that R is constant. So I can take it out, so that means that B is equal to mu naught I over 4 pi R squared integral ds cross with R hat. And then the next thing I recognize is that ds, the vector, and R hat, the vector, are perpendicular. So that means that I needn't worry about the angle between them. It's going to, you know, cos, the sine of that is going to equal 1, and R hat is equal to 1. So that justifies me saying B equals mu naught I over 4 pi R squared times the integral of ds. That's all I'm left with. And in this case, integral ds is equal to, what's it going to be in terms of expressions? It's going to be 2 pi r over 2. And if it was a third of a circle, 2 pi r over 3. If it was 16/17 of a circle, it'd be 2 pi r times 16/17. Okay, so that's pretty straightforward. So then this gives me mu naught I over 4 pi r squared times 2 pi r over 2, which equals mu naught I, the 2's cancel, pi over 4r. I think I'm right in doing that. Does my pi's cancel? Oh yeah, my pi's cancel, sorry. So that's that. So B is equal to, and looking at my numbers now, I say, okay, B is equal to, leave the mu naught alone. I is going to be 5 amps. over 4. And my r, my radius, 2. Times my mu naught, which equals 5 over 8 mu naught, which equals 5 eighths of 40, 6 eighths of 48, 0.6 of 48, 225 mu naught. And what would the units be? Magnetic field. Tesla. So there we have it. So it's not bad, especially if I give you it with the radius. Because if you think about it, I work out a terminology here which includes radius. Let's just talk for a minute. So this is a different thing. Suppose I give you the length. Suppose I gave L. You'd say the integral ds is equal to L, which you know, which equals, then you'd have to say how much of a circle is it? So I would have said 2 pi r over 2. So then because I know that value, I can find that value. Now you can substitute in for that. You could substitute L in. You do different cancelling. But you see how if you substitute that L in, you still got to work out what the R is. Okay? So you just got to play around with that. And the homework has examples going either way. Yeah? It's just sums. But it can be unfamiliar if you've not looked at it before the test. And I give you the L, it can throw you off. Okay? Cool. So a Boyer-Savart will be on the test. I can guarantee it. It's going to be on the test. Will not be a full circle, will not be a half circle. I doubt it anyway. It'll be some kind of fraction of the like. So this next one. So we did this a little bit with the electric field, didn't we? We kind of like want to know. Didn't we want to know the voltage at a certain point in relation to an electrostatic charge of... We're doing something somewhat similar. It's a similar construction. In this case, what we have is we have a circle of charge, of current actually, and we have a little ds that I'm interested in. And then I have, well, that creates a magnetic field. And remember that if that's my current through this wire, I cut the wire in two, and I'm looking at the end of it. And I have my magnetic field. My magnetic field goes like that. And so if I take a point of interest there, my magnetic field, if I take a point of interest there, my magnetic field is like that. So there's my little B caused by this piece of wire at that height there. So this is my little piece of wire, ds, looking from the side. And here's my axis. That's my axis there. And here's my point of interest. And so my magnetic field is kind of like that. And so every one of these guys is going to give a little magnetic bit. And they're going to form a cone of vectors. Because the piece of wire here will form this guy. The piece of wire here will form one down like this. The piece of wire here would form one out like that. Piece of wire. So it'd form a cone. Yeah? So, all right, I'm going to have to take that into account because they're not scalars. Voltage was a scalar. That was nice. These are vectors, but it's just a nice and symmetrical vector problem. And again, I wouldn't ask you this in a test to prove it, but this is what we're trying to prove. We're trying to prove this. It looks horrendous. But I look at this and I go, oh, yeah, I know what that is. What's that going to be from? What gives you this classic form? Pythagoras is going to be in here. It's like, I know where that comes from. So let's see what I have. So I turn around and say, okay, let's have a look. Use Boyer-Savart. So what was Boyer-Savart again? B is equal to, what was it? Mu naught I over 4 pi times the integral. Which way around was it? ds crossed with r hat over r squared. Yeah, so that's what we got. And let's have a look. So that's going to be from there. Let's take the okay. So I'm just thinking things through here. Okay. So in that case, then I want to find. Oh, let's get my dB is equal to mu naught I over 4 pi. And it's not going to be integral, it'll be the ds cross r hat over r squared. So that's that bit just for the one of them. And then I turn around and say, okay, so let's have a look. Let's have a look. I'm just trying to finagle my way through this. ds is, where's my r hat? My r hat is there, isn't it? Hat. So that means ds is perpendicular with r hat. That's that guy. And I know my well, let's have a look. So this equals, I'm just finagling a bit here, but I'm foundering a bit. So 4 pi, and this is going to be ds r hat sine phi over r squared. So this equals mu naught I over 4 pi. R squared is constant, so take that out. And my sine, that's going to be at 90 degrees to each other. ds cross r is going to be, it's going to be a circle. So it will be 2 pi r. So this would be mu naught I over 2r. Mu naught I over 2r. I think I just messed up, but let's have a look. Okay, so that gives me that guy, and I have to figure out if that is my dB, then I have to get my vector of dB. Look at this, that angle there is my alpha, and that angle there is my alpha. Oh, okay, I know what I'm doing. So, that means that my B is equal to, it's going to be mu naught times I over 2, and then my R is not going to be little r, it's going to be the square root of r squared plus x squared, which equals mu naught I over 2 r squared plus x squared to the half. Okay, that's that bit. And then let's have a look. I'm missing a bit. I'm missing a lot. So let me just have a quick. Can I cheat? No, I can't cheat. Okay. So I gotta stop for a minute. I'm gonna come back. No, I'm not gonna come. I'm gonna sweat it out and sort it out because I can do this. So B equals mu naught I over 4 pi integral of ds cross r over r. That's my basic expression. And that would give me my answer there. But my answer is over here, which is just further away. So that means that I get mu naught I over 4 pi integral of ds over r squared. So I'm going to, just bear with me a second. I'm going to clean this thing up a bit because I need to just slow down a bit. So I'm going to go back down to there, and I'm going to take all that out because I think I just walked off a cliff. You get to see my mind not working, so let's see how that goes. So that's going to be that, and then that goes to there. So there's my basic expression. So this equals mu naught I over 4 pi. My r is constant, but my r is going to be equal to the square root of r squared plus x squared times the integral of ds cross r of the integral of ds cross that. Okay? So, okay. Then I've got to turn around and say, okay, I'm going to say, by the same token, this is going to equal 1, and these guys are going to equal 90 degrees, because ds is still perpendicular to this r hat. So I'm going to say this equals mu naught I over 4 pi integral of r squared plus x squared, and this is going to be the integral of my integral of ds, and my integral of ds is my circumference. So my b is equal to mu naught I over 4 pi square root of r squared plus x squared. And now I need to do my circumference, and my circumference is 2 pi r. Okay, so I have that. So that is equal to the mu naught I square root of r squared plus x squared. Those 2's and those pi's 2. So I got that. Boom, boom, boom. So, and my r squared, my r has to stay on top. Yes, so that's that. Okay. 2 pi, 4 pi. Yes, I'm okay so far. You know, I, r. And then what I do is, so that is, but that is all these bits of it. So I have to turn around and take into account this angle, because I want that guy. So that is those guys, and I want to find that guy. So I've got to take the component of it. So I would say that if that was B prime and this was B, B prime equals B cosine that angle, the at angle, which equals B cosine. Well, what is the cosine of that angle? The cosine of this angle here is the cosine of that angle there, which is the adjacent, which is r, over the hypotenuse, which is the square root of r squared plus x squared. So this equals, take that guy, mu naught I r over 2 square root of r squared plus x squared, that's that guy, multiplied by r times the square root of r squared plus x squared. Oh, did I mess up a bit here? That should have been r squared, shouldn't it? Yeah? Yeah? So shouldn't that be r squared? Shouldn't that be r squared? Shouldn't that be r squared? Shouldn't that be? Oh, that shouldn't be. So that is squared. Ah! Sorry, I hate to sound so excited, but I am happy I'm here. So this equals mu naught I r squared over 2. And I have r squared plus x squared. It's not to the half. It's to the 3 over 2. So that's the 3 over 2. 1 half plus, yeah, 3 over 2. Well, I think that deserves a kind of like pat on my back. And a shame for me for not having it cold when I walked in, but, you know. So you got to see. So what did I do? I got myself into a hole, and then I stood back, and then I worked back from what I knew. It's very interesting that. Just want to. So I looked at that and I thought, man, I can't remember how to do this. And I was trying to remember. And when you try and remember, it tends to lead you off a cliff. So I walked off a cliff. And then I stopped. And I came back. And I said, let's apply Biosavat and just have faith in the system. And I just worked it out. It was not elegant, but it was there. Yes?
How did you get B prime?
How did I get B prime? Because from I know that B is that, because I just worked that out, yeah? And then I said, well, it's a component. So it's going to be adjacent over hypotenuse as a cosine. And so I looked at this and said, that angle there is the same as that angle there. And the adjacent is the r over the square root of r squared plus x squared. Yeah. That will not be on the test. Partly because there's nothing I can do with it. It's just all I can do is say, hey, you know, regurgitate this. So, but I want you to know it's doable. And I want you to kind of recognize the fact that it looks horrendous. And I certainly made heavy weather of it, but I knew it was going to be it wasn't like I said, oh, where did that 2/3 come from? I knew it was something to do with Pythagoras. Yeah? Cool. This tape will never get out of the room. It's like, okay. Magnetic force between two parallel currents. So, okay, we have two wires. Let's, not got enough space on here, but let's say we have two wires. So the current is flowing. Is that flowing towards me or away from me? Towards, yes. And is that one floating towards me or away from you? I just realized I've got to turn the lights off, haven't I? Oh, that's partly why we can't see so well. Oh, but not as well as that. Is that better? It is for me anyway. Is it better for you? There's no lights on. There's none of those at the back working. Okay. Okay, so we have these two currents coming, and then we use our right-hand rule. So will my magnetic field go in a clockwise or a counterclockwise direction around these two? Put your thumb in the direction of the current, and so clockwise or counterclockwise? Yeah, counterclockwise. So it kind of goes like that, doesn't it? That's my B. So as far as this guy is concerned, the I is coming towards me. So the B is up there, and the I is coming towards me. Now think back about what is current? It's the flow of... Now, do you remember we had an equation, didn't we? We had several equations. FB is equal to Q, V crossed with B. And there was another, wasn't there? There was FB is equal to, what was it, I? L cross B. Yeah. So those two, you can pick either one you like. I prefer the Q. So if the current is coming towards me, then the V is towards me, because the current is positive charge. So I point my fingers towards me, and then I curl them in the direction of B. Okay? So if the current's coming towards me I'm looking at this guy here. If the current's coming towards me and the B is pointing upwards because that's what's going on with this magnetic field, yeah? As it passes through this region, it's pointing upwards, then that means that my force is in that direction. Yep. Agreed? Let's do that one more time. So the current's going round, means that the magnetic field is up, and it's going to be V cross B. Can you see how the magnetic force is pushing towards the other wire? If I, up here, have the magnetic field coming towards me and this current's going in the opposite direction, the magnetic field is still upwards, but now the current is pointing away. So I point my fingers into the page as my V, and I curl towards my B, and my magnetic force is pointing in that direction. So can you see how these guys are going to be attractive if the two currents are in the same direction, and repulsive if they're in opposite directions? Can you see that? I'd like you to be able to remember that or recognize that. You know, work it out or know it. But I'd like you to know that conceptual thing. So I imagine that one of the wires creates the magnetic field that the other thing sits in. Then I say, all right, F equals Q V cross B. But if I want to know the actual force per unit length between these two guys, then I have to combine those. I end up with this equation. I don't derive it. And it is the force per unit length is an L. Force per unit length. It gets confused with the I. I'm sorry about that. Is equal to mu naught, the current going through the first wire, the current going through the second wire, over 2 pi A. And A is the distance between these two wires. So I say both wires carry a current in the same direction. The force is attractive. When the current in the wires flows in opposite directions, the force is repulsive. So this system is used to define the amp. So the amp used to be defined as the charge which flows when 1 coulomb of charge flows per second. So it was chemistry definition. And then people said that's an awful way of actually measuring it. I mean, at some point, somebody has to measure it. And the people in the United States who do that are the NIST, the National Institute for Science and Technology in Gaithersburg, Maryland. It's a big government lab. And they do that kind of thing. They set up what are called secondary standards, which are then used by industry to calibrate. So businesses, companies who make these kind of instruments will have secondary standards from NIST, which are certified, and then they will be able to guarantee, you know, our gauges are right, plus or minus 5%, or plus or minus 1%, or whatever. But somebody's got to be in charge of that. And so in this country, it's NIST. In Britain, it's the National Laboratory at Teddington Lock. All the different countries have their versions of it. So they're always looking for a better standard, something which is more easily reproduced. And chemistry is always a bit of an issue. So what they realized is, we can define the amp by saying when the magnitude of force per unit length between two long parallel wires that carry identical currents and are separated by 1 meter is 2 times 10 to the minus 7. This is going to be newtons per meter. The current in each wire is defined as an amp. So they basically use this as the way of defining it. You don't have to know that. I just want you to know that, you know, there's a secondary standard caused by that. Consider two parallel wires. One wire carries a current of 5 amps to the right, and a second wire carries a current of 4 amps to the left. They are separated by 2 meters. First of all, are the wires attracted towards or repelled by each other? And I refuse to remember stuff that I can figure out. So I'm just going to go dot, cross, that goes like, that goes like that. So there's my B. I have a B. I have a current going in, V. Point towards my V, curl towards my B. There's my F. So they are repelled by each other. Am I right? So I don't remember that. I figure that out. It's like, if you remember it, you're going to get it wrong sometimes. And then what is the magnitude of the force between two, force per unit length? So the force per unit length is equal to mu naught I1, I2 over 4 pi A. Was that right? Or was it 2 pi A? 2 pi A? Was it 2 pi A? So that equals mu naught. And it's going to be, the direction doesn't matter, 5 times 4 over 2 pi times a, and a is 2. So that equals 5 mu naught over pi. And in the test, I'd like you to work out what that is, but for today, I'm just going to leave it. Not with a mu naught, but with a pi. So this is equal to, well, what are the units going to be? Newtons per meter. Cool.
You said you wouldn't want us to keep pi below it?
I'd like you to just work it out. It's like, you know, leave the mu naught, but work the pi out. Just because some people put it in, some people don't, and then it's like, you know. Cool. Okay. That has been an hour. I'm going to take a 5-minute break. So let's just pause.